Hi, everyone. Welcome to the Scaling ML Predictions at DoorDash session. My name is Hing Liu, and I lead the ML platform team. In this presentation, I will present the first part, and Abbas, an engineer on my team, will present the second part. First, I will share a little bit about the DoorDash marketplace, then briefly talk about a few interesting machine learning use cases, then discuss some details about the approach and the strategies we use for building our ML platform. Abbas will talk about the main part of the presentation, which is the scaling ML online predictions. Then we'll wrap up with a few lessons learned and future work. DoorDash's mission is to grow and empower local economies. And we do that through a set of product offerings. First, delivery and pickup, where customers like you and me can order food on demand for breakfast, lunch, or dinner, or for various parties and similar occasions. Second, an emerging product called convenience and grocery, where customers can order non-food related items, such as flours, charcoals for the barbecue, or even sugar for baking cookies. The third product is called Dash Pass, a subscription product that is similar to the Amazon Prime. DoorDash also provides a logistics platform that powers the delivery for some of the notable merchants that you see in the slide, like Chipotle, Walmart, or Target. Now, DoorDash platform is a three-sided marketplace. And like most marketplaces, it has the flywheel effect, and we'll share some details about that. Now, starting at the center and moving to the right, as we bring on more customers, there'll be more orders, and that creates more earnings for Dashers. And that improves the delivery speed and efficiency for the marketplace. And now starting at the center and moving to the left. Again, as we have more customers, then there'll be more revenues for the merchants. The more merchants we have on the marketplace, the more selections there are for customers like you and me. Now, as this flywheel speeds up, it brings benefits to all three sides. Okay? It drives more growth for merchants, it creates greater earnings for Dashers, and brings convenience and selection for all of us as customers. Now, let's talk about the machine learning use cases at DoorDash. And I will describe these use cases by going through the food ordering steps, which consists of creating order, order checkout, dispatching order, and delivering order. Each of these steps has its own interesting machine learning use cases. Now let's start with creating order. This is where customers like you and me land on the home page and decide what to order, for breakfast, lunch, or dinner. So as far as recommendation goes, we would like to provide a personalized food ordering experience for our customers by surfacing up the best stores for them. For searching and ranking, when a customer searches for something like Italian food, we want to show the most relevant results and rank them in the respects of distance and quality. We don't want to show like restaurants that are like 40 or 50 miles away. At the bottom, you see a promotion from particular merchants. For merchants, we would like to help them to maximize their sales by providing targeted promotions of certain items at a certain time of the day. Onto the order checkout. Now at the top, based on the items on the shopping cart, we make recommendations about the side dishes that often go together. For example, if you order hamburgers and forgot to order fries, we'll make sure to recommend that. And at the bottom, this is related to fraud-related use cases. Like most internet e-commerce companies, we need to deal with the financial transactions and the credit card related issues. For the dispatching step, this is where the logistic engine kicks in. It sends the order to the merchants and it assigns the order to Dashers. The engine's primary job is to dispatch the right Dashers at the right time for the right delivery to maximize the marketplace efficiency. In terms of the food preparation time and the travel time estimate predictions, they have a few interesting nuances, such as traffic, weather, whereas we know we don't have much control of. Another interesting challenge in this area is, unlike Amazon orders, food orders emerge on the fly, and the food quality plays an important role in the delivery. Like the extra 5 minutes could be the difference between a great meal versus an awful meal. And for the last step, delivering the order. Regarding Dashers, the first step is how best to spend the right amount of money to bring on new Dashers onto the marketplace. And once they are onboarded, how to mobilize them to come out on a certain night of the week, or position Dashers at the right location to satisfy the demand on the marketplace. Now, in terms of the delivery assignment, we leverage machine learning to come up with optimal matching of Dashers to deliveries with these goals in mind, to ensure Dashers get more done in less time and consumers receive their orders quickly. The last use case is, once the food is delivered to the customer's doorstep, we would like to verify the accuracy of that delivery. Now let's move on and talk about our machine learning platform journey. Our journey started about a year ago when DoorDash decided to invest in building a centralized platform. As usual, different ML teams have slightly different needs, so it is very important to establish the buy-in from those teams on the idea of a centralized platform. One of the ways to do that is to have the representation from each of those teams, as well as an open forum to voice the collective needs, opinions, and also be open to the contributions to the development of the platform. The collaboration model we established includes Machine Learning Council that is responsible for making cross-functional team decisions, such as build versus buy. It also acts as a glue, which holds these different teams together so we can collaborate closely and learn from each other. Now, we don't claim this approach is the only right one, but the one that works for us so far. These are the pillars in our platform. They are modeled after the ML development process. It starts with feature engineering and then all the way to model predictions. The approach we use in building these pillars starts with thinking big, right? By working backward from the customers to put together a product vision document. Then building these pieces out incrementally based on the needs of the community while keeping an eye out for the long-term vision. Now, I will share some technical details about some of the pillars. Start with feature engineering. There are historical and real-time features. The historical features are generated from the Snowflake data warehouse and data lake. The feature service is responsible for uploading billions of features onto the feature store. And then for the real-time features, we build a framework on top of Apache Flink to generate this type of features, which are also written to the feature store. For model training and management, while in the exploratory stage, data scientists have the flexibility to train and iterate their models. But before deploying those models to production, those scripts need to be checked into Git, where our model training service pick them up and train the model, and finally store those models into our model store. We leverage the compute resources from the Databricks hosted platform to train our ML platform models. We also leverage ML flow for such as tracking experiment runs, training results, compute resources, library versions, and such. And finally, the model prediction pillar, where we have a centralized online prediction service that's based on Kotlin and C++. It supports tree-based as well as PyTorch models. And these models can be deployed easily via a runtime configuration. The prediction service can fetch features from the feature store if they're not provided in the prediction requests. And for the prediction results, I'll log into the data lake for data scientists to analyze and train the models. The next section will cover interesting challenges with supporting high QPS prediction use cases. Now, I would like to hand over to Abbas to talk about the interesting scaling challenges of our online predictions.
Thanks, Ian, for a comprehensive overview of the machine learning platform at DoorDash. Hi, everyone. My name is Arbaz, and I am excited to share this journey of scaling online predictions. Just a quick word on why it's critical to consider online predictions in an ML platform for scaling. In the graphics that you're seeing before, there were two kinds of workflows, online and offline. So the online predictions act as a bridge between practicing ML and applying it to the real world use cases. When you go close to a real world application, that's when stakes get high. System failure in online world could mean anything from a slow degradation to a complete website takedown. And that's why it's important to address scaling needs and reliability of online predictions much more than the offline ones. So when people think about scaling online predictions who are starting in this domain or new in this domain, they ask this question that, isn't scaling online predictions same as scaling any other microservice if you're considering a microservice-based architecture? The answer is yes and no. Yes, because a prediction service, it lives in a microservice framework. It is implemented as a microservice. It does these database operations, but it has these unique challenges that require a specialized treatment. Let me enumerate these challenges so that you get an understanding here. First, typically, prediction requests have larger payloads. It is because each of these requests have dozens of features that need to be passed in. And it's also a common practice to batch multiple prediction requests into a single request, because at times you're not just making one prediction, you're making multiple predictions for rendering a single page, for instance. And as a result, the payload size increases. It could be anywhere from tens of kilobytes to hundreds. And second, you need to make model computations which are intense, but are still within the same tight SLA constraints as any other microservice would have. And third, there's one interesting way how prediction workflow is different is that apart from production traffic, there's also experiment traffic. Data scientists or machine learning engineers, they keep running shadow tests or A/B tests to evaluate their models, which adds a factor of traffic into the overall consideration. And finally, auditing. Now, everyone needs auditing for ensuring compliance purposes, but here it's even more important because here a data scientist would use the auditing logs, that is the outputs that are that come out of the prediction request, to see if there are any issues in a deployed model in real time. They would also use these logs to further train their models, which is a critical need for improving their models. So you would ask here that, yes, I understand that there are these peculiar challenges you have to face when building services related to prediction, but what do you mean by scaling online predictions in this context? I would say that scaling can be best understood here from a user perspective. What are the users here? They are the data scientists, machine learning people, and the systems, that is the microservices, the upstream microservices that would call your prediction service. The data scientists will keep pushing newer models and newer features into production. They will also keep experimenting rapidly, which, as I said before, it adds to that traffic. It sort of multiplies the overall traffic by a factor. It calls for scaling. Hence, in terms of microservices, these are these other sets of upstream services that would call you. They want you to reliably support higher and higher QPS because the product is growing, or because there is a situational uptick in demand, either because there was this event that was happening. In our case, DoorDash, last year it was the pandemic, which was causing a boom in food delivery industry. It was also the IPO event for us, which increased their exposure and caused that situational uptick in demand. And so when you approach these needs of scaling, I believe you go through these different phases of scaling in the increasing order of intensity. In the initial phase, as you roll out the system and traffic picks up, you are in this happy phase where you could just like throw more instances, more workers and shards, and get the flow going as more traffic comes in. And the system will oblige happily. And then will come phase 2, where we would see that horizontal scaling has its limits. And we have to see that there are these users that are consuming more resources than the others. So to be able to continue horizontal scaling, they have to be isolated out. And after that, we just resume scaling until we can't anymore, because either our costs are shot through the roof or there are inherent efficiencies in our system. And so there is a need to optimize to survive. And then finally, since everything would not be in your control, once your services grow big enough, like really big, things that you couldn't control, such as the company's infrastructure, will start seeing major negative effects. You would be just left muttering, oh, infrastructure. And this might require a revamp of sorts or force throttling to survive at that stage. Now, my goal with this talk is to make you live these 4 phases through our experience that we had at DoorDash. And I want to share at what precise scales did we hit these phases and what did we do to transition from them. First phase, the happy phase, the horizontal scaling. Let me just chalk out the essential components that will be involved here. The feature store is a Redis cluster for us. It's deployed via AWS Elasticache. To be able to horizontally scale, we can just like increase shards on this cluster. The prediction microservice, as Hein mentioned before, it's a Kubernetes-based microservice. It's elastically scalable, can add more service replicas to it. The prediction store, it's a Snowflake table. We partition it by multiple relevant fields, such as date, model ID. And then the link between the service and the prediction store is mediated via stream processing to ensure high throughput. And we have a stream processor that can elastically scale its number of workers as the traffic grows through that bridge. So we were able to use this whole setup of horizontal scaling to add up to a system and handle more and more traffic. As you can see here, this graph shows how did we started trending upwards of 15,000 predictions per second by June of last year, starting at 1,000 predictions per second on March. Just like within a span of 3 months, we've grown 15x here, all on the basis of just like adding these workers, shards, or whatever. And then we observed that there are some models that consume more resources than the others. So just like posted a table here for our P95 latencies, Dasher dispatch, or like one of the highest latency models, it's 50 to 60x more than the lowest latency models. So you can see that there are more resources consumed by this high latency model, and the lower latency models start getting cannibalized. They will start seeing these degradation in their SLAs. So even though you're adding workers to the horizontal scaling setup, but the degradation does not get any better. So that's when we transitioned. That's how we transitioned to phase 2 at this point, where we realized that user isolation is the need of the hour. And we start to think that what could be the strategies of isolation that we can employ here. One is the thing that we were using, that we have all models live within one service deployment. It works when models are homogeneous in size and the usage patterns for these models are very similar, which is not often the case. And so there's this other approach that you can have one service deployment per model. Here, the concern will be costs primarily, because to be able to work in a cost-efficient manner, you need some sort of auto scaling in place, because every time you have this service running, hosting a model, if that model is not getting used, you are wasting those CPU hours. Auto scaling can help reduce that, but it needs to be working perfectly for you to get any cost-efficient system out there. The middle ground here is a hybrid approach, where some of the models can live within one single deployment, and you consciously take the decisions as to when to isolate. So there are multiple service deployments. Each service deployment can host multiple models. You would ask, that is this the way to go always? Because it does seem like it's best of the both worlds in terms of like it's cutting the costs and it's also mitigating bottlenecks. But the drawback here is that we need to be able to tell when to isolate here. And once we have isolated, we need to have an ability to determine that which models live where. Assuming that we were able to go past these drawbacks, or like we were able to have the system in place, you probably ask that, how far did this attempt take you in terms of your scaling endeavors? Was it a happy scaling life ever after? No, it was not. We were able to grow a big enough number though. We hit 6 figures in peak predictions per second, but we couldn't go as much higher as we had wanted to with this. We couldn't avoid a shard here to be the limiting factor. But one benefit that we got was that not every use case out there in our system was impacted because of one shard being overwhelmed. But it was a bad situation though, regardless, for the limiting shard. It started growing much faster than the others. We started hitting AWS hardware limits. We couldn't scale horizontally any further for this particular shard, but we still needed the predictions to keep flowing. And that's when we enter into the phase 3. So until at this point, scaling was merely doing more work, but to hit further and larger scales in a sustainable manner, the mission was to do more with less. So it's like doing more work with less resources. The most common example that I find here is a case of imperfect load balancing. Imagine you're adding workers, but because traffic is not evenly balanced, you're not shedding load off your existing workers. And the overwhelmed workers will continue acting as bottlenecks, no matter how many nodes you add. So optimizing load balancing here, in this case, is how you would scale to survive. So how did we holistically approach this? Was that we did these multiple optimizations at various layers, the microservice layer, the feature store layer. And the approach here was just to have this loop of observations and iterations. So for a microservice, an observation could look like you doing load testing, understanding the bottlenecks of how far the QPS can go before it starts breaking. You start to see also what are the latency profiles, what are the places where I'm spending the most time on. gRPC tracing was one such tool that came out helpful to us. We published on that as well in our blog. And we use these observations as a platform to make iterations on the There were these low-hanging fruits that we could readily adopt, such as some parameter tuning, that what parameters could be involved here. So these could be that what are the sizes of our payloads. If we are batching much more than desired, then we can cut the batch sizes. Or if we are not making use of the resources much, we can increase the batch sizes. We also tinkered with the timeouts on connections and what works better. And then there were these bandwidth optimization that we can think of either disabling them or enabling them. Then there was a few more involved optimizations, which were payload compression, compiler optimizations. All of these in together helped us improve the microservice layer. And then we advanced onto the feature store layer, try to see that the feature store that we had at that time, our Redis cluster, was it the best that we had? We did some benchmarking with a disk-based store to see that if a disk-based store can help us cut our costs or help us get more performance out. But this benchmarking helped us understand that a Redis cluster approach was the fastest and the cheapest one. So we had no other option but to optimize at the top of the existing implementation. So we took this approach of a complete schema redesign and see how can we make use of Redis in a better way, in a more performant way. The results were in line with that. We reduced our cluster costs by 3x or so, and also increased the performance by some of these optimizations. Again, this is also published in one of our blogs. So all these efforts, we breached 1 million predictions per second, the magic number, and the system was running stable all this time. This was a major accomplishment for us because we could use this the setup for quite some time. We were able to hold up traffic even up to like 2 million predictions per second. Was not obviously the end of our scaling attempts. We were at the cusp to explore what is anything in anything can happen. This is where we transition into the final phase that we're going to discuss. It's the phase at which we have started hitting scales that would impact the entire DoorDash infrastructure. So think of implications such as bringing all the services down at once because your service deployment went haywire. These are kind of implications that can happen when service grows that big. Just like enumerating furthermore that we encountered, our logging and metrics infrastructure stopped supporting us because we were hitting these limits that were not acceptable. Our third-party vendor segment for event processing blocked us for sending too many events because we breached the rate limits there as well. Our in-house service discovery module, console, threatened a total outage when one of our service deployments went on a continuous restart loop for the pods where they were constantly sending address update requests to console, which was also helping out the other services. And because console was overwhelmed, the other services were getting impacted. So yeah, this how we tackled all of them was just like take them one by one. For logging and metrics, we cut them to a bare minimum, like just log whatever we need at the bare minimum level. For metrics, we moved from a pull-based monitoring framework to a push-based monitoring framework to cut the cost there, to cut the number of events we were sending. We migrate away from a third-party streaming vendor to an in-house Kafka solution to have more control on the deployments, the cost, and the rate limits. We reduce our total number of pods to ease the load on service discovery by making them bigger. So instead of having a much larger number of pods, you have small number of pods, but bigger in size. With this conscious and sampled use of resources, we were able to hit much larger scales, north of 6 million predictions per second. Although this wasn't everything that we had wanted for, there were more scaling that we anticipate to come. And we're keeping an eye out on some of the bottlenecks here as well. We'll keep publishing or talking as we approach these higher and higher scales. So if you were to ask me in all this information that I have shared so far, what are the 3 key takeaways? First is that there should always be this understanding of when to isolate. We took the approach of isolating use cases wherever possible. And then secondly, every time we face a new scaling challenges, one easy way out is to just scale out. That is just like keep adding workers, keep adding nodes. That usually helps, especially in situations like Friday evening, there's high traffic, there's QPS increase, no worries, let's just scale out. But if you're constantly seeing more traffic than originally you planned for, it's time to introspect and see that how can you make the system better. Because if you don't, it will start to show up somewhere. The worst case, it will show up on the company's infrastructure and it will not impact just your service, but all the services out there. That was my part. Thanks for patiently hearing that. I will hand it over to Ian for carrying you through the last leg of this presentation.
Wow. Thank you, Abbas, for walking us through those fascinating challenges and how we tackle them. Here, we would like to share a few lessons learned. For Happy Path, as Abbas mentioned, the prediction service is a part of the user production traffic flow. So ideally, it shouldn't cause an outage if something went wrong, like fetching features and such. So therefore, it is very important to have the proper default values in place. In terms of customer obsession, in addition to work with them very closely with ML teams, we also strive to understand the business problems they're trying to solve, as well as the business impact. By having this understanding, it helps us in terms of the prioritization of our projects. For the last one, big vision and building incrementally. By building out our platform incrementally, it gives us the opportunities to receive feedback and also to make the necessary adjustments along the way. And this has been really helpful. In terms of future work, there's a lot to do, but here are the few that we are considering. For microservice optimization, As the prediction volume increases, and we expect that to happen in the near future, while looking into the potential caching the feature values, as well as prediction results. I'm sure there will be many interesting technical challenges in these two areas. Regarding generalized model serving, so far, most of the ML use cases are based on structured data. Moving forward, though, we'll see more use cases in the NLP and image recognitions. So therefore, we need to extend our platform to support those model types. And lastly, the unified prediction client. As the ML platform adoption increases, we want to provide an easier and optimized way of making prediction requests for our customers. So thank you for attending this session. And here's a link to the DoorDash engineering blog website, where you can find many interesting blogs about data science and machine learning.